So in this section, section 10.4, we're going to show how the ideas of tangent, normal vectors, and curvature can be used in physics to study the motion of an object, including its velocity and acceleration along a space curve. Now, here is the definition of velocity. And you can see that the definition is similar to the definition of a derivative that you learned back in Calculus 1, the derivative of a function. Only this is the derivative of a vector function. Okay, and velocity is equal to the derivative of your vector function, r prime of t. Absolutely amazing. And what they have here in figure 1 is an image of what they're talking about, a figure. Here you have position vectors r of t and r of t plus h. And if you were to take r of t plus h and add negative r of t, you would get a vector that is equal to the vector pq. Now they don't really have a vector drawn at pq, they just have a points p and q. But if you take r of t plus h plus negative r of t, which is the same as r of t plus h minus r of t, and then divide it by h, by a value of h, that's like a multiplying by a scalar 1 over h, you'll get that blue vector there. You'll get that blue vector. And as you let h get smaller and smaller, what's going to happen? The point q is going to approach the point p, and the blue vector is going to converge to that red r prime of t vector, which is your velocity vector. So, you know, remember, if you have an object moving along some path, okay, if you, So the velocity vector is always tangent to the space curve. And a way you can think about it is if you were to take like an object and attach it to a string and swing the object around as it's attached to the string. If you were to release the object would move off, would fly off in the direction of your velocity vector. Okay, how many recall that maybe from physics? It's a fairly straightforward concept. How many have seen that? Okay, Ellie's heard of that. And so I always think of that when I think of this figure. Okay, very simple idea. And if we want to, like here, in example 1, they say find acceleration given position. So here they have a position vector moving in a plane given by the position vector r of t equals t, has components t cubed and t squared. Finding the velocity vector means taking the derivative of r, and that just means you have a vector whose components are the derivatives of the component functions in r. And then acceleration, of course, is the derivative of velocity. Okay, are there any questions on that? Let's see, Fiona is asking, is the tangent vector, is the tangent vector of a position vector the velocity vector? Well, we got to be a little careful. The derivative of a position vector is the velocity vector. But there are lots of tangent vectors. I mean, the velocity vector is a tangent vector, but 3 times the velocity vector is also a tangent vector. So it is actually just the derivative. Yeah, you see what I'm saying. You see what I'm saying. Okay, so we get the velocity vector, the acceleration vector. There's the hold on here. Speed. Speed is the length of your velocity vector. That's called the speed. Okay. And they want you to evaluate all velocity, speed, and acceleration vectors when t equals 1. So when t equals 1, okay, this is what we end up getting then. So we just end up substituting t equals 1 for those vectors. And of course, the speed is root 13. Now, this example, well, yeah, if we were to look at a figure of this, here's a figure, figure 2. It shows the position vector, r of t, and at the point t equals 1, you're at the coordinate 1, 1, and they've drawn the velocity vector, which is tangent to the space curve at the point 1, 1. The velocity vector at time equals 1 is that vector's tangent to the space curve at time equals 1. And then there's an acceleration vector as well that they've drawn. That's just those vectors up there in yellow. Okay, are there any questions on that? All right, if you're good, let's proceed on. All right, let's go down a little bit here. Now, of course, you've seen problems similar to this. How many recall in Calculus 1 having an acceleration function, a of t, a function acceleration, and then you have some initial conditions on position and velocity, and from there you're able to integrate acceleration to get velocity, and then integrate velocity to get position. How many recall that kind of those kind of exercises way back in Calculus 1? Okay, Charles remembers it. I hope more than Charles remembers it. I've taught Calculus 1, and I covered those kind of problems. Okay, Ellie has. All right, good. So the integral of acceleration gives you velocity, and the integral of velocity gives you position. It's just the reverse of what you're used to. You're used to taking the derivative of position and getting velocity, and the derivative of velocity and getting acceleration. Well, now we're just going backwards, but we're doing it this time with vectors. So here you have an acceleration vector, which has components 4t, 6t, and 1. And if you want the velocity, you take the integral of the acceleration vector, and you integrate component by component, and then you have the constant vector. You have the constant vector, right, of integration, and you have to solve for that constant vector. Okay, well, to solve for the constant vector, we're going to make use of the initial conditions. Okay, so to determine, highlight it here, to determine the value of that constant vector c, we use the fact that at time equals 0, the velocity vector is I minus j plus k. And so if we substitute in t equals 0, okay, in that velocity above, that velocity vector above, and set it equal to I minus j plus k, we'll get that constant vector. Okay, we'll get it. And so now we write down our velocity vector. Okay, let's make sure. Please let me know if you have any questions. Hold on here. All right, hang on. Let me put this in. One moment. Let me go to the whiteboard, Yunu. Let me go to the whiteboard. Show you that. One moment. Let's see here. So, one moment here. So we're looking at example 3. And we have that the velocity vector at time t is equal to 2t. Hold on, let me try this again. I don't know why. Oh no, it gives different. Okay, just have to write it a little bit neater. Velocity vector is 2t squared I plus 3t squared j plus t times k plus c, that constant vector c. And we're told, we're given the initial condition that at time equals 0, the velocity vector is I minus j plus k. So that means then that the velocity vector at time equals 0, hold on here, it equals 2, so maybe I'll draw a little line here, 2 times 0 squared I, if I can get it to work, yeah, plus 3 times 0 squared j plus 0 k plus c. That's substituting t equals 0 in my velocity up there. Okay, that's going to equal I minus j plus k by virtue of that initial condition. Well, all of this here, okay, is just the 0 vector. Well, it's 0 I plus, well, it's just the, I'll just write this. It's just the 0 vector, okay? So that means that the only thing you're left with is c. So the c vector has to equal I minus j plus k. Let me see. Yes, that is correct. This is similar. This is similar to let me see here, 10.3. I think it might be. I don't know if it's 10.2. I know you've seen this in 10.2, section 10.2. You did this kind of exercise. Only you were just doing it with position vectors. Now we're doing it in terms of, I mean, you did the exercise, but now we're doing it in terms of our acceleration, velocity, and position functions. Yeah, v sub 0 is an initial condition. That's right. That's right. All right, good, Hunu. All right, you're welcome. All right, well, let's head back to the book now. So, okay. So now I incorporate that initial condition into my, I substitute it in the constant vector, which is equal to I minus j plus k. I substitute that in my velocity vector formula, and I end up with what you see here. Now I got to get position, so I have to integrate the velocity. If I integrate the velocity, here we go. I'm integrating it. Okay, I'm integrating it. And we're doing a similar process. We integrate the velocity function term by component by component. Okay. And we get a constant of integration, which is that vector d. That vector d. And so now we have to use the initial condition. We have to use the initial condition that we're given on the vector function r. And we're told that the vector function r has position equal to 1, 0, 0, which is the I vector. And so substitute t equals 0 and solve, and you'll get the d vector equals the I vector. And there you get r of t. Okay, are there any questions on that? All right, who's feeling comfortable so far with section 10.4? Okay, Ellie is. Good. All right, well let's proceed on. Let's proceed on. So the book has nice examples. The book has nice examples. Let me hold on. Figure 4. Yeah. Okay. I guess here they plotted the particle as well. And you know in what is it? MATLAB, you're able to plot space curves, right? You have a function or a MATLAB program to help you plot space curves. So you could plot this space curve, no problem, where t goes from 0 to 3. All right, let's proceed on here. Okay, so another concept that I think we should at least mention here is uniform circular motion. Okay, so an object that with mass m that moves in a circular path with constant angular speed omega has position vector r of t equals a times the cosine of omega t plus position vector r of t is a times the cosine of omega t times I plus a times the sine of omega t j. We recognize that moving in a circle, that parametric equations cosine and sine are going to be needed, right? And the a just lets the radius vary. So they want you to find the force acting on the object and show that it is directed towards the origin. Okay, so here to find force, okay, they seem to be wanting to find velocity and acceleration, those vectors. Why is that? How can we get the force from acceleration? Force equals mass times acceleration. That's right. So you got to get to the acceleration vector. And then Newton's second law says force equals mass times acceleration. And that follows for vectors as well. And so you substitute in you take mass and multiply it by the acceleration vector. And this is going to get you then down to here. But they note that the force, this force vector, is equal to negative m times omega squared times the position vector r of t. So this shows that force acts in the direction opposite to the radius vector r of t. Okay, it points inward towards the origin. Okay, so what kind of force is this? If an object's moving around in a circle, the force acting on the object is pointing inward to the center of the circle. What kind of force is that? Good, that's right, Hunu. Centripetal force. Centripetal force, and that's what they're showing here. Okay, that's what they're trying to talk about here. It's important. I think it's there's a figure as well. Okay, now they mentioned too about like an example 5 motion of a projectile. I'll let you look at that. I want to move onward here in this section and look at tangential and normal components of acceleration. Are there any questions on this example that we just did? Okay. Okay, well then let's move on here. Really beautiful stuff. Okay. Okay, hello everybody, I'm back. I'm sorry, a thunderstorm came along and I'm back. We're still recording here, so let me go ahead and get the WebAssign back, and we will continue where we left off, okay? Thank you for your patience. So this is okay, hang on here. I got to bring up the ebook again. Can everybody hear me okay? Just so, okay, good. Thank you. All right. Okay, we were in section 10. We are in section 10.4. Okay, let's bring that up. So maybe you made some friends here. Had a little time here to make friends, hopefully, in the class. And okay, tangential and normal components of acceleration. Okay, so key thing here. When we study the motion of a particle, it is often useful to resolve the acceleration into two components, one in the direction of the tangent vector and one in the direction of the normal vector. Put that over there. So we want to resolve the acceleration into two components, one in the direction of the tangent vector and the other in the direction of the normal vector. So how do we do this? Well, let's first of all look at the unit tangent vector. We know how it's defined, but since we know that the derivative of position vector is velocity, the unit tangent vector is really the same as the velocity divided by the speed at some time t. Okay, so what we can do, of course, is we can write the velocity vector as speed times that unit tangent vector. Now, if we want to get the acceleration vector, we take the derivative of the velocity vector. But taking the derivative of the speed function times the unit tangent vector on the right, the speed function, that v, which is it's a function of t, v on the right, the scale is a scalar function on the right, v, and then you have the unit tangent vector, which is a function of t. So if we're going to take the derivative of the velocity vector, we have to take the derivative of the right side. And what rule is going to be used to take the derivative of the right-hand side of the velocity vector? It's one of your derivative rules. Well, do we have a quotient there? Or do we have the product? That's right. That's right, Yunu. We're going to use the product rule. And so when we use the product rule, okay, here is using the product rule. See that? The velocity function multiplies every component of the unit tangent vector. And so the components of that entire vector are just the velocity function times the functions in the unit tangent vector. And so you use the product rule and get this. And it's a very useful expression, Now, what are we going to do next? Well, let's take a look at curvature. We talked about curvature in our last class last week. Curvature is defined as the length of the derivative of the unit tangent vector divided by the length of the derivative of the position vector. And of course, that is just equal to the length of the derivative of the tangent vector divided by the speed, v. Okay, I guess I'll refer to, yeah, let's just refer to that as the speed function, right? So that means then that the length of the derivative of that unit tangent vector is equal to the curvature kappa times the speed, Now, what we can do here is we can recognize that the normal vector, the normal unit vector, is just the derivative of the tangent vector divided by the length. The normal vector is the derivative of the unit tangent vector divided by, I'm not saying that right. The normal vector, maybe I'll highlight it here. The normal vector is equal to the derivative of the tangent vector divided by the length of the derivative of the tangent vector. And this means then that the derivative of the tangent vector, and we're focusing on that because it's one of the expressions in our acceleration vector, the derivative of the tangent vector is just equal, therefore, to the length of the derivative of the tangent vector times the normal vector, which is equal to the curvature times the speed times the normal vector. And so this means that you can, in the acceleration vector up here, you can replace on the right-hand side that second part that has the derivative of the tangent vector, you can replace that with the curvature times the speed times the normal vector. Okay, so you have in the acceleration vector on the right there, after the plus sign, you have the speed times the derivative of the tangent vector. But we're going to replace the derivative of the tangent vector. We're going to replace that with this expression here. And this means then that it turns out that the acceleration vector can be expressed as the sum of two vectors. The first vector being the derivative of the speed times the tangent vector. Okay, and by the way, what's the derivative of the speed? What's the derivative of speed equal to? Acceleration, that's right. Good. So the acceleration vector can be written as the acceleration times the tangent vector plus the curvature times the square of the speed times the normal vector. And pictorially, they have a nice picture below of this. Nice picture here. Maybe I can have it all in, well, yeah. Here's a picture. They've drawn the acceleration vector, and the acceleration vector, you see how it's in a plane that in figure 7, the acceleration vector is in a plane defined by, or a plane containing the tangent and normal vectors. You see that the acceleration vector is just a linear combination of the unit tangent and the unit normal vectors. And that's because of this result here. No, it isn't the parallelogram law, that we're using. It's just, well, so what they do though, is they say, well, let's define the acceleration as the tangential component of the acceleration vector. Okay, what they're doing is they're going to say, let's write a sub t and a sub n for tangential and normal components of acceleration. So then the acceleration vector is just the tangential component of acceleration, a sub t, times the tangent vector, plus the normal component of acceleration, a sub n, times the normal vector. And of course, the there are your tangential and normal components of acceleration. Okay, so this really makes, okay, good. And if we go down here to the picture, okay, there's the acceleration vector. Okay, there's the acceleration vector, which is a linear combination of the unit tangent and unit normal vectors. Now, let me ask you if so there's an influence in the acceleration vector is influenced. I mean, what influences the acceleration vector? Does the magnitude of acceleration influence the acceleration vector? In other words, does the v prime? It does, absolutely. And does curvature affect the acceleration vector? It does. And you can see based on the figure there that if you're moving along a path and the path has more curvature, the acceleration vector is influenced more by the normal vector that goes inward. You see that? You see how that in other words, think of it like this. Okay, here's your acceleration vector. If the curvature is increased, if kappa is increased, does the normal vector have more, does that second component that has the normal vector, does it have a greater influence on the acceleration vector if curvature is increased, if curvature is more? It does. In other words, your acceleration vector, right, the greater the curvature, the more the acceleration vector is pointing in the direction of that normal vector that goes inward. That's what I'm trying to say. And I'm just trying to see here if I mean, they have a little discussion below. Okay, so it makes sense if we look towards the middle of the paragraph. It makes sense, this idea that the acceleration vector is a linear combination of the unit tangent and unit normal vectors, where the curvature kappa influences, the more the curvature, the more the normal vector is an influence on the acceleration vector in terms of the direction of the acceleration vector. This makes sense that if I look at this yellow paragraph, if I go down a little bit towards, let me see, the 6th line, it says this makes sense if we think of a passenger in a car. A sharp turn in a road means a large value of curvature, and so the component of acceleration perpendicular to the motion is large, and the passenger is thrown against the car door. Okay, how many maybe have learned that in physics class? this kind of idea, where they talk about and maybe it's your first time seeing it, and that's okay. But keep in mind, when you're being thrown against the car door, it's not because if you're accelerating around a turn, how many have had that experience? I hope, you know, I want you to be safe, but I'm just going to ask, how many have had, okay, Yunu's gone around a turn fast, and Malik has, and you get pushed against the door. But that doesn't mean that you are being flown outward from, you know, from the center. What's happening is the car is moving inward. It's moving inward. The car, the normal, the component of acceleration pointing in the direction of the normal vector. Okay, let me get that picture up. Hold on here. Okay, the component of the acceleration vector pointing in the direction of the normal vector is the car is moving in the direction of that normal vector, not all the way, but it's moving inward. That normal vector has a bigger influence on the acceleration vector when you are moving faster around a curve. But your body hits the door, but really what's happening is the car is moving inward towards the acceleration vector is moving inward, and that's why you're getting hit against the door. Okay, how many maybe learned that in a physics class? I don't know if that's something that that you might have learned in a physics class. Okay, Ellie recalls that. Kyunu recalls that. Okay, all right. So very good, very good. Okay, all right. So I'll mention a few more things here. I want to get you. I'm going to have you do a little work here, but I want to point out something here. They talk about, like, for instance, these tangential and normal components of acceleration. They have formulas. They show how to derive them, but there are formulas to compute them that are easy to use. There's the tangential formula. There's the normal formula. Absolutely amazing. Okay. And also in the book, they do talk about Kepler's laws of planetary motion. Okay, these are Kepler's laws. How many have seen Kepler's laws? Maybe in a class, another class. Okay, Charles has, and Gordon has a bit. And what they do, Ian says regrettably, they discuss in the book Kepler's laws of planetary motion in terms of vectors. Okay, like for instance, let me just hold on here. Yeah, the law of gravitation. The law of gravitation. Okay, here are some. We already saw the second law of motion, force equals mass times acceleration. How many have seen the law of gravitation in terms of vectors? Okay, and so they talk about Kepler's laws in section 10.4, and we're, you know, this is not a formal physics class. I'm going to leave that to the physics professors, but sorry, I'm going to leave that to the physics professors to talk about that. But if you have time, it's a pretty interesting read, looking at all of these, you know, how they're going to prove, for instance, here, they're going to prove, and there's more to the proof, but they're going to prove Kepler's first law of motion, and they go through a proof here, an actual proof, you know, an actual proof. So, you know, it might be worth looking at. There's more to the proof. I just highlighted a little bit. Hold on here. Let me remove the highlight. Yeah, to prove sorry. Let's get it right. Yeah, to prove Kepler's first law And then they go through a proof there. They go through a proof. And, you know, it's pretty interesting stuff for sure. But are there any questions? I'm going to stop there. I'm going to stop there. I think we've talked about 10.4 pretty well. Are there any questions? Okay, I'll stop the recording.